So, we derived up to this, and from here what we need to do is, so we what we do is we take this particular term which is del f del q y dot delta q y dot, and see this is there is a time derivative here, and what we have derived in the beginning of the first lecture, that t and delta, they can be standard derivative and this virtual displacement curly derivative, they can be interchanged. So, if this is the case, what we can do is we can write this term as del f del q y dot d dt of delta q y. Okay, we can do that. Also, this thing, this whole thing can be written as d dt of del f right del q y dot delta q y, right, minus d dt of del f del q y dot del f del q y dot delta q y, right. This we can do, and if we, so in place of this one, if I substitute this into this integration, what I get is delta I is equal to integration t1 to t2 del f del q y minus d dt of del f del q y dot whole delta q y dt plus there is an additional term which will be t1 to t2 of. So, basically I took this term and this term. So, this term will be there, which will be given as del f del q y dot delta q y whole dt and multiplied by dt, right. Fine. Now, this term is a total time derivative term. So, integration of this term will simply give you, okay, I will remove this part, do not need this. So, if I just focus on this term now, if I, this is a total time derivative. So, it will be d of, so basically dt dt we can get rid of. So, integration d of this term, which will give you del f, sorry, q y dot delta q y between 1 and 2. Now, first and the last points are fixed, starting and end points are fixed points. So, any, oh, that one thing I forgot to mention, this parameter alpha is equal to 0 at the alpha n I is was equal to, so delta of q I was equal to alpha n I, right. So, n I were the, or it was alpha del q y del alpha at alpha equal to 0. Now, there is no variation of the starting and the end points. So, that means this quantity at delta q I at t equal to t1 is equal to 0 as equal to delta q I of t equal to t2. So, that means eta I, this is equivalent of saying eta I at t equal to t1 and eta I at t1 and eta I at t2 is equal to 0 for all values of I. So, the variation of the parameters are not there is no variation in the parameter at the starting and the end point. Now, if this is the case, this will be del f del q y dot evaluated at t equal to t1 and delta q y evaluated at t equal to t1 minus same thing evaluated at t equal to t2, but this is equal to 0 and the second term which will be delta q y evaluated at t equal to t2 will also be equal to 0. And this is how the variation is defined. I mean, the integration is defined, we can have variation in between the fixed points. If the fixed points are varying, that it makes no sense. So, the fixed points are fixed. Okay. So, we have variation in between, at the fixed point this will vanish. Now, if this is 0, so if this is the case, this integration is unanimously equal to 0, right. So, if this is 0, then what do we have? Okay. We can get rid of this one and we are left with this, right. Now, if delta I is equal to 0 along as we see in the variation principle. What is the variation principle? Once again, the variation principle for a mechanical system is, right now we are talking about mechanical system, which turned out to be true for any other system, that delta S, which is delta of L dt between fixed point t1 and t2 has to be equal to 0. So, if right now we are not talking about we are not specifying the functional nature of f. So, we are not talking about principle of least action for say, but we are saying that delta of I, this particular integral will be equal to 0. Now, if this is the case, then we immediately see that it can an integration, this is basically an integration, and the integration can vanish if and only if the integrand is equal to 0 and the integrand is actually this, right. Please remember that there is a summation over all the q y's. Okay. So, if this is equal to 0, so we have a situation which we have a very familiar situation of sum over I del f del q y minus d dt of del f del q y dot is multiplied by delta q y is equal to 0. And from there, because stating that q y's are independent, stating that q y's are independent, we can equate all the coefficients of each of delta q y term to equal to 0. We have done that during Lagrangian, right. So, now we have seen that it is not only for a mechanical system, but if we can define a proper function for proper functional form of f, it could be Lagrangian, it could be total potential energy, it could be the time traveled between these two paths, two fixed points, whichever parameter we want to optimize. If delta I has to be equal to 0, okay, delta I equal to 0, I mean the variation of this particular integral, if we said that variation of this particular integral equal to 0, we get the same set of familiar equation, which is this. Of course, there is a problem of negative sign, but that is not a problem because we have 0 anyway. So, we get back the same set of equations, similar looking equation. If we set f equivalent to L, then we get back the standard Lagrange's equation of motion, starting from principle of least action. And so, basically if we start from principle of least action, taking this f is equal to L, we get back familiar form of Lagrange's equation, right. So, Lagrange's equation, although we got it previously, we got it starting from D'Alembert's principle, this is lot more fundamental, because here we do not have any prior knowledge. I mean, for example, what we did was we started from Newtonian equation, we removed the forces of constraint, then we introduced generalized coordinate. After so many steps, we got this equation, just replace F with L. Okay. But here what we are doing is we are starting from a principle which is more fundamental in nature, and we are getting back the same equation, same set of equation without having any specific knowledge of the Lagrangian. Okay. Now, this is called the principle of least action, as I have already mentioned. The quantity S equal to L dt between T1 and T2 is called the action of a system, and it is not only for mechanical system, but also it has been found, it has been shown later on that these are also equally valid for quantum mechanical systems, equally valid for systems which are moving at very high velocity. Very high means towards the speed of light. So, that means in general systems where general or special relativistic theorems are applicable, quantum field theories are applicable. Everywhere this action integration is a very important parameter. So, a system will follow a certain path along which the action is 0 or variation of the action is 0, or rather say I would say action is stationary. Okay, that is the most general statement we can make at this point. So, out of this so many paths, the system will choose one path along which this quantity, this integration is, the variation of this integration is equal to 0, right, and this will lead to an equation of this particular form. Okay. Now, we will take up examples one by one, and right now there is no formal, I mean we do not want to carry forward from here. We can do lot more things in terms of Hamilton-Jacobi equations, and if we can go into special relativity and all, this principle has way more applications than we could even think of. But right now that is not the objective. I wanted to introduce you with the principle of variation calculus. We will now take up some specific examples and check for its applicability and of course, we will take systems which are not only dynamic in nature, we will also take up static systems. Okay. All we need to do is we need to find out a suitable form of F. For a dynamical system, if we want to follow the dynamics of the system and find out which path it will take in the configuration space, we have to take the Lagrangian. But if you are not looking for the dynamics, for example, as I said, I want to prove formally that the shortest distance between 2 points on a plane or in space is a straight line. Now, it so happens that shortest distance between 2 points can always be framed into a plane, right. If there are no other constraints, I can connect any 2 points in this world by a plane. I mean we can make them sit on a single plane. So, when we are talking about shortest distance between 2 points, we are talking about shortest distance between 2 points in a staying in an Euclidean plane, right, strictly speaking. Anyway, I will come back to that, but let us look into the problem set I have prepared for you. The first problem is a small problem on point transformation, which I will solve, but I mean it is very easy to solve actually. So, the problem says, so for a one dimensional systems, it is possible to incorporate viscous damping. So, I am talking about simple harmonic oscillators, by the way, I forgot to mention, I should say one dimensional simple harmonic oscillators. It is possible to incorporate viscous damping without writing a dissipation function. Lagrangian is L, which is e to the, and what we do is we just add a e to the power minus gamma t term with the Lagrangian, and this will take care of the damping. Now, we suppose there is a point transformation S is equal to e to the power minus gamma t of q. What is the effective Lagrangian in S, and we also have to find out the equation of motion. Okay. So, we start, okay, we will come back to this. We will come back to this very soon, but let us start with this simple problem. So, we have a Lagrangian L, which is, so it is problem number 1 of the problem set, e to the power minus gamma t q dot square by twice m, m q dot square by 2 minus k q square by 2. So, this part is standard one dimensional simple harmonic oscillator Hamiltonian. We add a damping term here. what good practice would be to find out the equation of motion for this Hamiltonian without altering anything, right. Now, what we do is, but right now what we are doing is there is a point transformation of S, which is e to the power minus gamma or gamma t q. So, we have to find out L prime, which is a function of S dot, right. So, this is our objective. So, we start by writing this equation and taking gamma e to the power gamma t in this side. So, we just write e to the power gamma t S. So, q dot will be e to the power, so this is 1 and q dot will be gamma e to the power gamma t S plus S dot e to the power gamma t, right. So, this is the derivative. Now, we have to square both of them. So, the first term tells you that q square is simply e to the power 2 gamma t S S square, and q dot square will have 3 terms. So, it will be gamma square e to the power 2 gamma t. Actually, e to the power 2 gamma t will be common from both all 3 terms. So, I am just writing it out. So, it will be gamma square S S square plus S dot square plus 2 gamma S dot, right. Now, we can think of writing L prime, which will be e to the power minus gamma t m by 2 q dot square, which will be this. So, you see we have e to the power 2 gamma t in both the square terms. So, what we can do is we can take out e to the power 2 gamma t, which if I operate this 2, it will be simply e to the power gamma t, not minus, right, e to the power gamma t, and inside we will have. So, we do not worry about the exponential term, which we have already taken care, we have modified it. So, inside we will have m by 2 gamma square S S square plus S dot square plus 2 gamma S S dot, that is the first term, minus k S S square by 2, right. So, this is your L prime. So, you see L and L prime, they have different forms in a point transformation, but both of them are equally valid Lagrangian. So, you take, what you can do is, as I said, you calculate the equation of motion from here, and we are going to calculate the equation of motion from this one. So, the second part is we have to do d dt of del L del S dot minus del L del S, which is, okay, this is little longer. We can do that, but I think you can also do it yourself, because we have one S dot term here, S dot term here, and please remember each of the term will be multiplied by an e to the power gamma t. Okay. So, finally, I will write the final answer. Oh no, it is okay, we can do it, maybe one more step. I can do del S dot, which will be simply e to the power gamma t multiplied by m S dot, sorry, is it right? Yeah, it will be m S dot plus this term, 2 will cancel out, m gamma S, right. So, if I take d dt of this term, this will be d dt of this whole thing here. So, the first we have to take out gamma e to the power gamma t m S dot plus m gamma S, and we have to add e to the power gamma t m S double dot. So, first we took derivative of this term and multiplied it here. Second term is this is fixed and derivative of this term. So, this is m S double dot plus m gamma s dot, right, and del L del S will be, okay, you can see del L del S will be from this term and this term, right. So, we have once again e to the power gamma t m by 2, sorry 2 will cancel out. So, it will be m s gamma square m s plus 2 will cancel out. So, it will be m gamma s dot, right. So, if I subtract, sorry, if I subtract one from the other just to get the final equation, so this will be equal to 0, you will definitely get the final form. So, I am leaving it to you. It will be, so what will happen is e to the power gamma t will, you can take out from both the equations, you get one gamma ms, this gamma will go in, yeah. So, you can basically take gamma e to the power gamma t common and then you can simplify. So, you will get back the familiar equation of simple harmonic oscillation with damping. Okay. So, this was little lengthy, but rather easy problem. I selected this problem specially because I wanted to give you an idea of point transformation, because theoretically sometimes it is very, it is not very convincing, it is always better to do an example. So, I hope I have convinced you that point transformation is something which is not very difficult, maybe it has a formal name, but this is something that we have done already, we have already known for some time. Okay. Now, let us come back to the principle of variation. Right. Problem number 2. Okay. So, problem number 2 is the principle of variation, which we have to demonstrate the shortest distance between 2 points on a plane is a straight line. Now, on a plane we should not write on a plane, either we should just say 2 points, or we should say 2 points on an Euclidean plane, because we can have we can go along the surface of some some sphere or some cylinder, that is also a plane, right. So, when we say plane, we talk about Euclidean plane. Okay. So, what is the distance L between 2 points? We have one point here, one point here, right. So, if we should not draw a straight line, because this is something we have to prove here. So, let us say this is a curve which joins these two, right. So, what we do is we take a small length element d l on this curve. Now, in a 2D xy plane, d l is equal to dx square plus dy square whole root, right. So, L, the total length will be integration of dl, right. Of course, there will be limits 1 and 2, but that is not terribly important here. So, if I write this for dl, what we can do is we can take out dx and we can write this as 1 plus dy dx whole square. So, once we do that, and oh, by the way, one thing I should say, that I have a function f of, so far we have dealt with functions of t, q and q dot, let us say. Okay. So, here t is the independent parameter, q is a dependent parameter which happen to be a coordinate in this case, and q dot is nothing but dq dt, right. So, we can and we have proved that if I have a if I have to optimize the integral, or we have to have a stationary integral, then this should follow equation which is d dt of del f del q dot minus del f del q equal to 0. Of course, I can extend it to n number of parameters and put q y and q y dot, that is not the point here. So, what I am trying to tell you is, instead of this 3, if I have these 3 parameters, if I have any function which will be a function of x, y and dy dx, which we will call y dashed, there also using the same same set of mathematics which we have followed, we can say that d dx for stationary integrals, d dx of del f del y dashed minus del f del y will be equal to 0, right. So, this we can do. So, t will be equivalent of x, which are independent parameters, y or rather q will be equivalent to y, and of course, q dot will be equivalent to y prime. So, we can extend our variation principle or whatever the principle of stationary variation to a case which is non-mechanical in nature. These are for mechanical system and these are for any general system where I have one independent parameter, one independent component, one parameter, one dependent component and the derivative of a dependent component. So, following the same logic here, we see dx is our independent component. So, this is nothing but integration dx between 1 to 2 root over 1 plus y dash square, right, is not it. So, if this is the case, immediately we can identify this function. Now, so where f of x y y prime is equal to root over 1 plus y dash square, right. Now, this function is not explicit dependent on x or y dashed, but that is not our problem. This is our function. Now, if this is the function, it will follow this set of equation, this equation, right. So, what we want to do here, we want to calculate the minimal distance, that means either maximum or minimum. Right now, we are talking about minimum. Minimum is also minimum will be achieved when this integration, the length. So, please do not mix it up with the Lagrangian. Okay, let me write dl, small l, that will be easier. So, this integration delta L will be equal to 0, right. Only then we will have the shortest length, and for shortest length. So, if this integral is equal to 0, the function f has to follow or follow this particular equation. I mean, this particular equation will follow. So, let us try this. Del f del y prime will be equal to, so it will be 1 plus y s square to the power 3 to the power half. So, it will be 1 by 1 plus y dash square to the power half times 2 y dashed, right. So, this is del f del y square y dot y dashed, okay, and del f del y is equal to 0. So, what we get is by applying this equation that d dt of this, so this is equal to 0. So, d dt of d dx of this is equal to d dx of this whole thing will be equal to 0, right. This is equal to 0. So, that means this is equal to a constant, right. So, we can write this equal to some constant c. Now, if I simplify from here, so what I have is, if I take square from both of this, so we get 4 y prime square is equal to c square plus c square y prime square, right. Or also we can call c square a new, I mean we can just absorb c and c square, yeah. So, if we want, I can put root c, that is just for my convenience. This is an arbitrary constant anyway. So, if I change sides, we get y dash square into 4 minus c is equal to some other constant. So, essentially what we get from here is y dashed, which is dy dx is equal to some new constant k, just by changing sides. So, it will be root over c by 4 minus c, which we can call k, and that is it. So, if I integrate this, we get y equal to familiar form of y equal to mx plus c, and this will be equation of a straight line, right. And now, we have formally proved using variation calculus that the shortest distance on a plane between two points on a plane or on an Euclidean plane is a straight line. Please remember, this is the first formal proof of this statement, which you have been heard, you have known since you were in maybe primary school, 3rd standard, 4th standard. That is where it started, or maybe junior high school, 5th or 6th standard. And now, at this age, coming into your bachelor's course or master's course, you have finally formally proved it. Okay. So, this is the beauty of variation calculus. Many things we just take it, which we have taken for granted. This is the beauty of advanced study. Many things which were taken for granted at the time can now be proved more formally. Right. So, this is one, and I think we have just enough time for one more short calculation. Let us see what do we have. Okay. So, we have another problem, problem number 3, but I think in order to perform this problem, we need to learn an identity which is called the Beltrami identity. Okay. So, we will end this class by proving Beltrami identity. Now, what is this? Okay. So, just give me a second. Right, dx. Right. So, Beltrami identity says if this function x y y prime is not an explicit function of x, that means if del f del x is equal to 0, okay, then we have f minus y prime del f del y prime is equal to a constant. So, this is an identity which of course can be proved formally, which we will do in a moment, which is extremely helpful when we are discussing calculus of variation, extremely helpful. So, we will end this class by proving this identity, which is essentially a 3 line proof. So, to begin with, we have this equation del f del x y dashed minus del f del y is equal to 0. Oh, please remember, this f is not any arbitrary function, but f is the function for which this equation is valid. Okay. So, this is the function which comes out as a stationary, as a function of stationary integral. So, it is not true for any arbitrary function. Okay. So, if this is the case, and please remember that f is a function of x y y prime. So, df dx is given as del f del x plus del f del y y prime plus del f, or sorry, yeah, it is fine, del f del y prime d y prime dx, right. Okay. Or we can call this the last term, we can simply call y double dashed, right. We can simply call that. Okay. Now, this is, let us call this equation 1. Now, what we can do is we can change sides and write del f del y y prime is equal to df dx minus del f del x minus del f del y prime y w prime. Okay. Now, what we can do is we can multiply this with y prime and write it down here. So, it will be minus del f del y y prime. I am writing this term first. Changing sides, it will be equal. So, it does not matter, we do not need the minus, will be d dx of del f del y prime, right. So, comparing the right hand side, what we can do is, okay, so it is slightly, okay, so we do not need this one anymore. So, slight mathematical jugglery we have to perform. What we can do is we can take, so basically if I subtract one from the other, then this side will be equal to 0, and so we can write d dx of del f del y prime is equal to so df dx minus del f del x minus del f del y prime y double prime. Okay, and these okay, one more step, and what we can do is del f del y double prime. Right. Little bit modification, and this can be written as, so sorry, I do not remember this by heart, but it is not very difficult anyway. Y double prime, this f minus this, okay, sorry, d d f of f, right, because I have this one and this one in hand, sorry, it will be y prime, yeah. So, if I compare this two, it can be equated with del f del x. Okay, let me check this step once more. So, if I open this bracket, so it is first term will be df dx, which is there, second term will be d dx of df del f del y prime times, oh there, yeah, that is what I was missing, there will be a y prime dot here, yeah. So, now it all fits, good. So, just manipulate this little bit and you can write it in this form. Now, going back to this identity, if this side is equal to 0, if this is equal to 0, then we immediately see this whole thing equal to 0, and we get f minus del f del y prime is equal to a constant. Okay, very good. So, we proved it. It is a very easy proof, 3 or 4 lines essentially. So, this is called Beltrami identity. Please keep this in mind, because we will be using this on and off. I mean, whenever needed, whenever we find a function f which is not an explicit function of x, we can use this identity. We can just do this for the problem we have just now we have solved. Please remember that in that problem also f was not a function of x. So, what I would suggest is, instead of doing what we did, you can just apply this identity and see if you get the same answer. Of course, you will get the same answer, there is not a question, but this will be a good check for you. Okay. So, with this we end this lecture here. Next class we will continue with this problem set. We have few more problems to solve, which will take more or less the full class, and definitely we will start with the introduction of our last topic, which is small oscillation. Thank you.